the QFT and USR inflation and recent developments. Thank you. Okay.
Yeah, thank you very much. And I just want to share my slides if possible.
Okay.
But always we have some problems, technical problems in doing.
By the way, I like your hair.
Yeah. Thank you very much. Yours as well. Thank you. Just let me find the button, share my slide. Yes. And maybe I can use this one. So
yes,
maybe
now we can see the slides.
Good. So I want to, if possible, I want to go to whole screen. And if anybody has questions, please maybe let our chair and he will let me know. And then if you don't mind, yeah, I can interrupt and then go through the talk. Thank you.
Thank you.
Okay, just let me, I have a little problem with my internet. Good. Okay. Okay, so maybe you have my slide, yes? You have my slides, yes?
Yes, yes.
Okay, great. Thank you.
Yes, we can see.
Okay. Hello again, everybody. Thank you very much. In Tehran, we say good afternoon, but other side of the earth, I don't know. Good morning, good evening, or good even good evening. Like so. Okay, thank you very much for providing this opportunity to discuss our recent findings and the challenges that raised for loop corrections in early university studies, say for USR inflation or ultra-slow roll inflation. So I will try to discuss the normalization of quantum fields in this background. Here is the, you can see the address of our two recent papers with Hassan Firuzjahi and Amina Sirirad, my colleagues, and we went through the studies of this problem. Okay, because I will talk a lot of infinities today, and also in Rogina talk you here about infinities. I took this poetry of poet William Blake. If I remember correctly, he is Breton. If the doors of perception were cleansed, everything would appear to man as it is, infinite. So I like it. I always use this quote to emphasize on the importance of infinity, and specifically in my talk today. Okay, here is the plan. A very brief QFT refresher for young researchers and why we need ultra-slow roll inflation or ultra-slow roll inflation, and why it does matter for our early university studies, and also for the mode functions and vacuums and renormalization and regularization. I will try to discuss. I will try to discuss these matters and the vertices and the maybe infinities and loop corrections, but I will go through. I will consider just one loop corrections, not higher orders, and maybe if one wants, he can go through higher order loop corrections. Okay. Just let me. Okay, here maybe some introductory books for young students. One of them, which I like it, is the Bogolyubov and Shirokov book, and another one, maybe one of among the best ones, is Quantum Field Theory of Peskin and Schroeder, and a more advanced one is the Quantum Field Theory of Steven Weinberg, late Steven Weinberg. If you want to consider gravity for your calculations, I mean, studying quantum fields in the presence of gravity, maybe the book by Professor Buchbinder and Shapiro is a good suggestion. So here I will talk about the quantization and why we need quantization and what is the vacuums and the difference of different vacuums in flat space-time or curved space-time or in the presence of interaction. So it does matter. So we need to take care of regularization and renormalization and make connection between these two vacuums. For instance, as you can see, I hear two figures of Gogolyobov and one of Weinberg. So usually Weinberg studies in-out quantum field theory for useful for scattering. And Gogolyobov finds a way to make a connection between different vacuums, usually named as Gogolyobov transformation or Gogolyobov coefficients. So I sandwiched Weinberg between the state of Weinberg between two states of Gogolyobov. So after calculations, one can find the relation between these vacuums. And here in the right panel, I bring maybe, I don't know if you know him or no, but he is renowned in quantum field theory for curved spacetime, Leonard Parker. In the 1960s, he made a lot of progress of renormalization, and also he introduced the particle production due to the presence of gravity for quantum fields. Okay, but as you know, we have a lot of figures in the progress and putting forward the quantum field theory, like Dirac, like Schrödinger, like Schrödinger, like Pauli, Heisenberg. Many figures we can name here, and they particularly played a crucial role in making progress of quantum field theory, and specifically for electromagnetic field at first. Then they went through studying other fields like fermionic field or like so. And they faced some problems, some infinities in their studies. And some leading scientists like Feynman or Veltman or Gerard 't Hooft, they found their renormalization solutions for dealing with infinities and their problems. Okay. Maybe I can ask a master question for my study today. This master question is simple and short, and one can ask, can small-scale quantum effects, true loop corrections, leave an observable or detectable imprint on large CMB scales? This is precisely the sort of question, for instance, Weinberg framed when he developed the N-informalism, which today I will use this mechanism frequently, for cosmological corrections. Okay, here simply I will review the inflationary mechanism and also the reason why we need, the reason behind primordial black hole formation and USR inflation. As you know, we can focus on USR because it can amplify short scale curvature perturbations dramatically. And it is a mechanism often invoked to produce primordial black holes and also large Langauer-Schmidt. So it was, if I remember correctly, first time was introduced by William Kenny from Buffalo University in USA. And he devised this mechanism to explain the large non-Gaussianities. Then the scientists understood that it can be useful to justify the primordial black hole formations. So the challenge today, this model is faced, is when you study the quantum loop corrections, higher order loop corrections, it maybe affect this era, and so you will produce a lot of primordial black holes, and maybe even it can forbid this process. So I will try to discuss this mechanism today. Here, as you can see, this is the mode functions can be responsible for observable CMB. Here, you can consider 15, for example, EFOL numbers. Here is just 3, 4 EFOLs, and here is the last phase. Here we call it second slow phase, which inflated going to be in the attractor phase, and here is the end of inflation. Then maybe you have some mechanisms like preheating, reheating, and then you expect it going to be smoothly connected to the radiation era. But it is not my concern. I just worry about this area that was labeled by these small black bullets. Okay, great. So let me review what is the problem and why we need such corrections, and what is the mode functions, and like so. In brief, I will review this problem. Okay, as you know, in a realistic model of inflation, the inflaton, the scalar field is responsible for inflation. We call it inflaton. Inflaton trajectory maybe can undergoes a short USR maybe epoch, which, as I said, is sandwiched between two slow roll phases. And the sharpness and the duration of these transitions can control how strongly small scale modes couple to the larger scales. So I try to answer my master questions. As you know, in a standard slow roll model, as I said, curvature modes freezes with a roughly constant amplitude. In the USR, the curvature perturbation grows on superhorizon scales, as you can see from this figure. Here is the waves, they are deep inside horizon, can be considered as quantum corrections, small modes. And here is the horizon, and the upper solid line, which K over AH is almost 1. The modes going to be as large, can be treated as large modes, and going to be classic modes. And they are, when they go past the horizon, then they can be considered as freezed modes, which carry a lot of information. And today we can observe the results based on these modes. But maybe the question is that, is it possible these modes, these small modes, specifically in the USR era, affect this large CMB modes? Okay, and here is the transition. It depends if you transit very quickly from USR phase to a slow roll phase, or midly, because it can be important to discuss and to obtain the physical results. So today we will consider the sharp one, this gray one. Okay, and this parameter H is responsible for this transition, and can be introduced based on the slow roll parameters to the end of inflation here, as you can see. Okay, great. We can review quickly what is a slow roll phase or what is USR phase. This, as you can see in this red block, when you have phi double dot plus 3 H phi dot, we call it USR because potential going to be constant here. The evolution of potential can be put away, and we just worry to solve this equation, simple equation. And if you consider friction and the evolution of the field, we have a slow roll phase. So the parameters can be explained, the first and second slow roll parameters can be explained using these differences, and I try to divide these two stages of our evolution in the early universe studies. Okay, so if your background is a de Sitter spacetime, so you have gravity, and I want to now study quantum fields in this configuration, in this background. So as you can see, there are some beautiful modifications, and meanwhile, some challenges. We need to cope with these challenges. Great. Sorry. As you know, the choice of vacuums, as I say, and the separation of the scales, almost they are frame dependent, specifically in curved spacetime, and carefully specifying the vacuums and the matching conditions across these transitions should be taken into account, and so they are very important. Regarding these problems and these challenges, we have right now 3 different categories in studying today are running. So there are 3 major maybe categories in these studies. The first group, which we are included, they claim that one loop corrections from enhanced short modes can be parametrically large and even non-perturbatively. Maybe they make some problems for perturbative quantum field theory. So you need to employ some non-perturbative approaches like stochastic field theory or stochastic mechanism or lattice field theory, which for the stochastic we employed. And in our second paper here, in our recent paper, we showed that even when you employed stochastic and non-perturbative approaches, maybe you have some loop corrections that you need to be worried about these corrections. And the category B or the category 2, they claim that when boundaries or other like geometric corrections came to the game, maybe, and when they handle carefully, they expect that they cancel, for example, the corrections, loop corrections, due to the boundaries, due to some extra terms, I don't know, like topological actions they add. They expect that we have cancellation of loop correction, which it is a little weird because maybe you need some fine tuning to remove the corrections. There are some maybe groups that they are in the middle. They are not extreme cancellation or growth. They believe that due to epsilon corrections, maybe when your transition is mild and it is not sudden and sharp, yes, maybe you have some epsilon first slow roll parameter, epsilon suppressed corrections. So there are some references that you can maybe later you can go to study or see the problems raised. Okay, here I can try to briefly introduce my formalism. Not my formalism, the configuration that I study my problem there. As you know, we don't have a complete version of quantum gravity, so we need some effective version of field theories, a lower energy of that total and global quantum gravity. We can still employ some effective field theories, which maybe, if I remember correctly, for the first time introduced by Steven Weinberg, then other people like other scientists like Senatore or other guys, they try to study effective field theories. And it is a very powerful tool to study quantum fields because it allows you, fortunately, to study higher order corrections step by step and maybe iteratively, so people can consider safely these loop corrections. As you know, from the effective field theory perspective, the approach, as I said, maybe championed conceptually by Weinberg, and he used frequently in modern cosmology, and maybe we can consider it as a triumph of effective field theory because it can predict some observations very nice and safely. Okay, right now, due to symmetry breaking, as you know, we have some Goldstone bosons, and we can write down the perturbative part of your field according to these Goldstone bosons. As you know, we have not enough time to explain all the details, but you can consider this as your action of matter, which pi is your Goldstone bosons and n is Laplace function according to Android, Meissner, or 1+3 decomposition. And here you can see the dot is for the conformal time, for instance, or for cosmic time, then prime is for conformal time, and I runs for spatial derivation. Here is the Hubble constant or Hubble parameter, higher order of differentiation in this red frame. And without any exaggeration, and it was for the first time that the quartic part of this action was considered by Firujahi in 2023. And before that, 1 year before that, Cristiano and his supervisor in Japan, they introduced, but they just considered the tree action, the cubic action here. You can see we have this free, the S2 is for free part, S pi third is the cubic part of the action, which is responsible for studies the vertices of order 3 in quantum field theory. And here you have see pi 4 is for quartic. I will let you know in next slides what they are. Okay, here if you have some modes, they are in interacting phases. For instance, you have two study loop corrections if you want to obtain a good picture of your configuration. You need to study these loop corrections, higher order loop corrections. So when you have two modes with momentum k1, and then here you can see a loop correction of order 3, which can be studied by H3 here. And also the last one is for the tadpoles or zero modes, which some people claim that if you study the tadpoles, then they can be considered to cancel the loop corrections, which we checked this claim, and we didn't observe any cancellation. And for this is simpler, this H4 is simpler. And for these diagrams, which is Feynman diagram of these interactions, we need this H4. Okay, for higher order loop corrections, maybe you need higher order Hamiltonians, so like H5, H6, but it is beyond of the scope of this study today. So just I want maybe satisfy myself with this one loop corrections. Okay, but why they are important? Why Goldstone bosons are important? Because we can find a relationship between these loop corrections. These Goldstone bosons and curvature perturbation. Here is by calligraph R, which we use this definition, but just this red one is leading, and other terms they are subleading in our studies. So we just we are lucky, so we just need to employ this red one to study the 2-point function or higher order point functions like 3-point functions, 4-point functions for curvature perturbation, to study the statistics of these modes, and then we can compare our result with observations, for example, with CMB or like so. Okay. I don't know if there is any question or no. I can continue my slides.
Yeah, you can continue, please.
Oh, okay.
Thank you.
Good. Okay, as you know, as I said, when you have two different vacuums, here I labeled by omega and not. Not goes for three modes, and for background, I mean, and omega is for interacting parts because we have interacting. So we need to find a way to make a connection between these two different vacuums, and usually we can use the renowned NN or Schwinger-Keldysh formalism, which here
I think he lost his connection.
Seems he's
he's here. Hello, Professor. Are you here?
No, he's not here. Will come soon. But I think there is a question in chat box.
Yeah, I will ask that questions. Let's first he can finish his talk.
I don't know what happened to my.
Yeah, you lost your connection. Yeah.
Sorry. Okay. Okay, as I explained, when you have two different types of vacuums, you need to make a connection between these vacuums. And,
Professor, I'm sorry for interrupting. So there is one question in the chat box. So
okay, good.
First of all, can you check the questions?
Oh, okay, sure.
Is it time to answer this question, or you can leave it to the end if you want?
Okay, just let me message. Maybe I lost the questions.
Yeah. Okay, I will copy and paste. I will copy and paste.
Thank you.
Can you see it now?
Is one loop correction coming just from scalar field inflation considered right? No one loop correction coming from. Yes, maybe loop corrections can be considered for different modes, for scalars, for vectors like electromagnetic fields, for instance, and also for gravity, for graviton modes. So some like I remember some papers like Pinol and Firuzjahi and Ballesteros, they studied separately the effect of loop corrections in when you have, for instance, two scalar fields. They come and loop correction come from gravity. Yes, they studied, but you need to take the leading terms, because sometimes you have suppression due to the as I said, epsilon suppression, like so. So you need to take care of these calculations. But today I just worry about the scalar fields. Maybe in some future works, yes, we can go to true study the graviton interaction with scalar fields, or models like DBI, or alpha attractor, or some fields that scalar field has interaction with gravity or vector field. Okay, I hope it was enough. Okay, so we have to employ the informalism, which is a powerful tool, is perturbative. And here you have T bar, which is for anti-time ordered, and T is for time ordered. And this operator O is the operator that should be studied using this approach. It is good for calculating 2-point, 3-point, or 4-point functions. Okay, we can then using some techniques, some mathematical techniques like series, then we can obtain at least up to order 2. This one is for free part when you have no interaction. For example, your potential is off, or like so, for scattering if you want to study particle physics. But in inflation, as you say, as I said, in is completely different from in out. You need to some extra calculations to make a connection. Specifically, it can be done using the Bogolyubov transformations to make a connection between in and out, or interacting or non-interacting cases. This one is of order, the blue one is of order 2, because you have just one Hamiltonian, or the operator that should be studied. And here you have some technicality, because you can see the red one. I don't know, you see the cursor or no, the pointer like so. I moved here in the second line. You have the upper and lower bounds of integral runs from tau naught to tau. But when you have a real part, you have tau naught to tau 1, then tau naught to tau. We call it usually nested integrals. Here, if you want to study loop corrections for this one, you have such nested integrals, which I promise you is very complicated. But this one runs for just not nested integral, so is a little simpler than that one. And this one also, maybe you need, no, this one also is simpler than that. This one is complete and complicated, so there are some complexity, so you need to take care of nested integrals. Okay, whereas we have 3 different phases and 2 transitions, 2 barriers, we need to calculate both functions for different eras. So we have from the start of inflation to the start of USR phase, we obtain this one I labeled by RK1. RK2 is for USR phase, and let me no, yes, RK2 for USR phase, and RK3 for maybe SR2 phase. And using matching conditions, or like Israel junctions, you can obtain the coefficients of these mode functions. Here you can obtain these coefficients. So when you obtain your mode function, then you can compute the 2-point functions, for instance, here. Okay, for the quartic action, I mean for that simple Feynman diagram, you can calculate the 2-point functions. I labeled by omega h4. So just let me one time show you again this diagram, this one, that labeled by orange arrow. So h4, I mean, I want to calculate that diagram. When you calculate that diagram and employ the definition of Hamiltonian and mode functions, you obtain such integral. When I1, I2, and I3 is defined according to these definitions. Okay, you see a lot of mathematics, sorry, but I just want to explain the complexity and also then the results. Don't worry, for the first sketch, you no need to understand all the complexities. Just, for instance, take care of the different times we have, tau, tau naught, and tau prime, for instance, here. And it goes from deep inside horizon, relabeled by -infinity, to end of inflation, 0. And so right now I can ask a question of myself. So what we did up to now? As you know, in the past 3 years, more than 200 papers devoted to this problem. But almost, I can confidently say that almost they didn't renormalize or regularize these integrals satisfactorily. They just, for instance, used some hard cutoffs, and then they obtained their solution. And how they treated the infinities, it is not clear. So we claim that we are the first team that we cope with these problems. And me and my colleague Nasir Rad, we studied the renormalization of these integrals. And after renormalization, we captured the corrections. And we didn't observe any cancellation. So because when you want to study quantum field theory, you need to renormalize your calculations, regularize the infinities. And even sometimes it depends which model you employ. For instance, point splitting or cutoff regularization, and I mean running cutoff, not hard cutoff, and dimensional regularization. There are many methods can be carried out, like adiabatic regularization invented by Parker. So one needs to calculate integrals and remove infinities, then he can claim that his result is carried down in quantum field theory. Okay, and here after the calculations, because our action has some parts, you can see accordingly some corrections. This one is for the bulk part. This one is for, again, for the bulk part here, for instance, and here. And you can see that the correction is to e to 6 delta n, which delta n is the duration of USR phase. So when your phase is a little like 4 or 5 Eiffels, so you have some corrections which is of the order of background solutions. So is a little complicated because our method is perturbative. So what happened? How your correction is of the order of background. Some people, and also we, believe that it may be affect the perturbative studies, and so you need to employ other models that we did in our recent work. We did it using the stochastic method, and we developed and we devised a method that our noise extended to non-Gaussian mode. As far as I know, we were the first team that also referenced by the renowned scientist in stochastic recently, Vincent Winning, and he also justify our claim that when you want to capture loop corrections, your noise in a stochastic model should be non-Gaussian, not simply Gaussian. So there are some technicalities maybe we can discuss later. Okay, for the transition,
I think we should summarize the talk because we have only 1 or 2 minutes left.
Okay, sure. No worry.
Sorry for interrupting.
Good. Sure. And also here for the quartic part, which is the maybe in 5 minutes I will finish. Is it fine?
I think it's fine.
Thank you very much. Thank you. And for the quartic, for the cubic action, we have some complexities because you need to carry it out very maybe safely and with you should be patient because it maybe takes 2-3 years of your time when you want to study quantum field theory in the presence of gravity for inflation, for instance, because even it's maybe you consider it like a joke, no problem, because one of our integrals, when we carry it out, it contains 18,000 terms. 18,000 terms. It took 6 months of 2 researchers to purify those complicated integrals. Then they took these results here. Is for different terms in your integrals. Then again, you have corrections and we didn't see any cancellation. So our 2-point function has the loop corrections. They are of order of background. So maybe some people believe that you need to calculate the lattice field theory, but other teams, some teams from Switzerland, they carried out for some simple cases that they showed that yes, you have loop corrections and they are growing. And for 2 loop corrections, maybe you have e to the power of 12. We checked some cases because for 2 loop corrections you have 27 Feynman diagrams. 27 Feynman diagrams. 11 of them, they are ordinary 2 loop corrections, and almost 16 of them, they are tadpoles that should be carried out, and maybe it needs more time to be finished. Okay, great. And also here you can see the calculation of the tadpoles. And again, we have some loop corrections of those order, and again there is no cancellation. And these log terms, they are interesting because when m runs to infinity, you have some maybe infinities, but we just want to show how we can deal with these infinities. One of those infinities is these log terms. So one maybe need to introduce some counter terms to cancel this. You are familiar with this process. I just want to emphasize the physics. Okay, so I can skip this concluding results, and there are some references we used, and you see almost they are for 24, 23, and maybe 25, and right now still it is running and is a hot topic of research because there are some contradictions and some problems that should be fixed, and still maybe it's a turbulence era of quantum field theory. Okay,
I think it's better to say thank, right?
Okay,
Thank you very much, Professor. for excellent work. And I think we may get small questions if you have one here. Is there anybody has a question? I think no. Thanks again.
Yeah, thank you very much for your time.
Thank you. Thank
Yeah.
you.